For the last part of this lesson, I really want to focus in on the rational function where the degree of the numerator, the top, is bigger than the denominator, bigger than the bottom. And I want to focus in on finding the end behavior asymptote, the slant or the oblique asymptote, as we call it. It doesn't really have a horizontal asymptote because it doesn't approach a number, it approaches some other function. So I'd like to look at an example of that and then an application problem. All right, so suppose I'm given a rational function, f of x, which is x cubed minus 3x squared plus 3x plus 1 over x minus 1. So clearly we've got an example where the degree of the numerator is bigger than the denominator. Now, the other things still apply. The zeros of my denominator, in other words, when x equals 1, I'm going to have a vertical asymptote there. Do not cross line. Constant over constant, my y-intercept is going to be -1. If I factor this, I can find the zeros of my, the x-intercepts rather, where the x-intercepts are, or the zeros of my numerator. And right now I want to focus in on the horizontal, what happens in the slant or oblique, because I've got the degree of the numerator is bigger than the denominator. So I need to do synthetic division to find that quotient. Well, I suppose I could do synthetic division. I'm actually going to do long division here. X minus 1, x cubed minus 3x squared plus 3x plus 1. All right, so let's see. What times x gives me x cubed? X squared. X squared times x gives me x cubed, but it also gives me x squared times -1 is negative x squared. Now we subtract. X cubed minus x cubed is nothing. 3x squared minus negative x squared is 3x squared plus x squared, which gives me -2x squared. And bring down the 3x. What times x gives me -2x squared? Negative 2x. Negative 2x times x gives me -2x squared. Negative 2x times -1 gives me plus 2x. Subtract. Negative 2x squared minus -2x squared, nothing. 3x take away 2x is x. Bring down the 1. What times x gives me x? 1 gives me x. 1 times is -1. Subtract 1 minus a -1. No, they don't cancel each other out. I get 2. But that's my remainder. I can think of that as plus 2 over x minus 1. And I don't care about that as far as the slant asymptote goes. So I'm looking at the quotient up here. And the slant asymptote will be the curve y equals x squared minus 2x plus 1. So other than just a line, this is going to a parabola. Let's take a look at it graphically. So clear out the things from the previous lesson. And I'm going to plug in my original function in y1. So open parentheses, x cubed minus 3x squared plus 3x plus 1, close parentheses, divided by, open parentheses, x minus 1, close parentheses. And look at it at a standard viewing window so I can take a look at this strange function here. And you can see that I've got this part. Remember we said the y-intercept was -1. We can see that here. The x-intercept, if I set this equal to 0 and solved, apparently I'm only going to get one of those. The vertical asymptote at 1, here's 1. I can see that I've got a vertical asymptote there. Let me change the window a little bit. I'm going to do my x's. I'm just going to do from -5 to 5 on my x's. So from -5 to 5. I just want to stretch it out a little bit so that I can see these things. There we go. So my first thought is, do I have an asymptote here, or what do I have? And it's actually a quadratic. So I'd like to graph this on top of the function now. So y and y2, I'm going to graph x squared minus 2x plus 1 and graph the end behavior asymptote, and there it is. So we can see that the function is approaching the asymptote, function's approaching the parabola as x is increased without bound and as x is decreased without bound. Now, strictly speaking, as x is increased without bound, the value of the function increases without bound. As x is decreased without bound, the value of the function is also increasing without bound. But this is the asymptote. The function values are getting closer and closer and closer to this curve right here. That's my end behavior asymptote. As we saw with the concentration problems, the end behavior asymptotes often have some sort of real-world meaning. Let's take a look at a sample problem now. So in this problem, we have a farmer that wants to make a 200 square yard field. But the farmer wants to use the minimum amount of fencing possible. And we're going to make it a rectangle too. So the farmer wants to make a field that is 200 square yards, a 200 square yard field. Now, it's going to be in the shape of a rectangle. If not, the most optimal solution would be a circle. So the shape of a rectangle, and I want to have the least perimeter. The perimeter would represent the fencing, and if the fencing is very expensive, the farmer wants to keep the cost as small as possible. All right, so let's take a look at what information do we have here. Well, if I draw a diagram of this situation, and let's say here's my farmer's field, and what do I know about that? Well, I'm going to say that this is x and that this is y. The perimeter would be 2 lengths and 2 widths. Well, that doesn't really work for me. I can't maximize or minimize this. I've got many variables in there. Well, what else do I know? Well, I want the area to be 200. Well, I know that the area is length x times width. Or x times the width here, x times y, if you will. Let me go back and change these to y's. And I know the area has to be 200. So 200 equals x times y. If I solve this for y is going to be 200 over x. And that's what I'm going to substitute in here. So now I've got a perimeter function as a function of x, the length right here, is going to be 2x plus 2 times y, but y is 200 over x. And you can see this is a rational function here. The perimeter is a function of x, 2x plus 400 over x. I could multiply by x over x, and I could put it in standard form, 2x squared plus 400 all over x. But I'm going to do the rest of this on the calculator. I want to know for what value of x am I going to get a minimum value here for the perimeter. What value of x will give me the smallest possible perimeter here? So as I take a look at this function, I'm going to graph it. Open my y equals. Now, at first we might not realize, well, what type of graph are we going to look at? After we graph it on here, I'll sketch it here and talk about y. And I'm going to write it down exactly without simplifying it. So 2x plus 400 divided by x. Now, what type of window? Well, x represents the width. Having 0 doesn't make any sense, so I'm going to go from 0 to something, to some other width. What could the possible width be? Let's try going from 0 to maybe 20, scaled in ones. The y represents the perimeter. I know the perimeter, the whole perimeter here, as a function of x, is going to be, I don't know what it's going to be. So maybe go to a perimeter of maybe 0, or no, that's the scale, scaled in ones. Minimum 0 to maybe 200, scaled in 25s. And then I'm going to graph this. This is what I was expecting. I want to change the window though, so let's go back to the window and make the x a little bit bigger. Make the x go to 50. So the x's from 0 to 50 scaled in 5s, and then the y's 0 to 200 should be plenty, scaled in 25s. Now here's the graph that we're seeing. And why are we seeing this? We're seeing something that looks like this. This, the x down here, represents the width of the field. The y value, p of x, represents the perimeter. So as the width gets smaller and smaller and smaller, the length is getting longer and longer and longer. The area, the perimeter gets bigger. And as the width gets bigger and bigger and bigger, the perimeter gets bigger and bigger and bigger. Here is my minimum value. We can see it on the graph here. That's what I'm going to need to find. This point right here will tell me what value of x will give me the minimum perimeter possible, the smallest perimeter. So I'm going to solve, and these types of problems, you're going to see this type of curve. Playing around with the window is always an issue. What window am I going to use? But I'm going to calculate now the minimum value there, calculate minimum. I'm using a TI, so I have to drop the pins on either side of it. Casio users just G-solve minimum, and it'll jump right there. I'm going to drop a pin over here, go to where the other place of the minimum is, obviously over there somewhere. And I get a coordinate of 14.14, comma, 56.57. So what does this mean? This means when my x value is 14.14, I'm going to get the smallest possible perimeter. The smallest perimeter is 56.57. What's the unit associated with that? Yards. So that's the smallest. What would the dimensions of my field be? Well, I know it's going to be 14.4 times something times whatever that is. How do I find the y value? Here's a formula for that. So I'm going to do 200 divided by 14.14, and the y value is also going to be 14.14. So if I have a square, 14.14 by 14.14, I will have an area of 200 square yards and the smallest possible perimeter. Okay. So if I want to find the dimensions, the answer is going to be 14.14 yards by 14.14 yards. If I want to find out what is the smallest perimeter, 56.57 yards. And you'll see other problems. Draw the diagram, just like with the maximum and minimum, the optimization problems. Draw a diagram. What's your lengths? What's your widths? Or what's the distance, your distance formula, whatever equation, formula, graph you're using, do that. And then this is going to be the graph that we're going to see, and we're going to find minimum values in here. Or it might go the other way, and we're trying to find maximum values. But it's all going to happen right here in the first quadrant. All right, so go ahead and start the homework now. We did a lot today. Good luck. And remember, you can always leave questions in the comment section.